Welcome, public inventors. Welcome, everybody. I'd like to demonstrate the latest version of the Glussbot or Gluss-based robot, which I am building. Let me get it started while I talk here. So, as you can see, I've done some more 3D printing and produced more of the so-called turret joints. And I'd like to point out that I have now learned that the turret joint was previously invented in 1999 by Song, Kwon, and Kim and patented. So it is not an invention on my part, although I was unaware of it when I created it. The turret joint should really be ascribed to Song, Kwon, and Kim. You can find a reference to that in my materials. I don't know if they ever actually constructed it, as I have. What you're looking at right now is that I've programmed the Glussbot to move this point in a square in Cartesian coordinates, which is a little hard to see. But basically, it's moving in a square and then moving up 10 millimeters at a time. So it should go up right now. Oh, it's finished. Let me set it going again. I have it make 5 squares. Each should be 10 millimeters higher than the other. So basically my program within the Arduino has mapped the space of the Fregeli actuators into a millimeter-based Cartesian coordinate. The shape, which this point is capable of assuming, is not in fact a cube in 3 spaces. It's a very complicated shape representing the intersection of 3 spherical shells. So it's not necessarily cubic, and the purpose isn't really to be cubic, but I wanted to get the math worked out to show that I could do that and program a single point to move in a Cartesian space. So what you're seeing here is the octahedron. This is an octahedron attached to the tetrahedron. So the whole thing becomes an octet in the original patent by Buckminster Fuller in 1961. That is, this is an octahedra tetrahedral structure. And if you had many of these, you could fill space with them. That is, they fit together in such a way as to fill all space. You'll note that it looks as if, and it is true, that the bottom area can sit on a plane and the top area can sit on a plane. And that's pretty much the way Buckminster Fuller created that truss, to build a large truss which spans space between 2 planes. So it sort of creates a slab shape. Let me set another test program going. So this demonstrates the joint by moving through the extremal positions of the actuators, not the, so that's the extreme contraction point, and I haven't tested this, it might fall off the table, rather than moving in a Cartesian space. This is moving through the extreme point of all of the thing. By the way, this little spring hanging here is for us to put the electronics in an enclosure so that the electronics will sit inside this tetrahedron and be protected from bumping into other things. And we'll do the same over here. Now, obviously, much of this is constructed out of these carbon fiber rods rather than actuators. I've ordered some more actuators to make it more flexible, but I think this shows how you could make a large, light structure, because, of course, this is really quite light. It's just made out of plastic and carbon fiber. And in fact, I can replace each rod with an actuator as I develop the electronics for it and and I purchase the actuator. So hopefully this gives a little better idea of how the whole thing could work. I personally find it a sort of attractive and fascinating shape. You can see the octahedral shape here with one tetrahedral face extended. One of the things that I'm thinking about doing is building a walking robot by taking that tetrahedra here and extending it to this face and this face and that face, and then in that way have 4 legs. So this would become the top of the walking robot. It's my goal to sort of get that done. So thank you.